Thank you. Welcome on this glorious World Golf Day. I'm going to talk about how you create secrets with a combination of measured boot and verified boot. And, well, this is me, as you can see. Let's see. This is better, I think. What happens? This is strange. Sorry. Something just locked up. Ooh, this is interesting. Okay. It's a kernel bug, perhaps. No, my pointer is still moving, so it's something Wayland, something. Damn. What's this? Come on. Do I have to reboot this thing? This is silly. Yeah. Yeah. Right. Let's see. No, it's still. Ja. Fortfarande hängd här inne. Så det här är intressant. Så om jag gör så där då. Ingen konsol heller. Ja, vad fan. Ja, ja, intressant. Ja, okej. Vi får robot om den. Ja, okej.
I'd just like to say that we still have a bit of room for lightning talks. So if you want to do like a 5-10 minute thing on any subject that might interest the audience, just come and talk to us and we can just put together a little schedule for the lightning talks. It's always fun. It doesn't have to be super well prepared, but if you have like a problem or if you've done something lately that you'd like to share, please go ahead.
And it doesn't have to be 5 minutes. It can be 2 minutes if you can formulate your problem in that small space of time.
Yeah.
Yeah. Anyways, anybody heard any good jokes?
Well, as they used to say about Sun workstations, at least they boot fast. So this is me hugging a VT100 terminal, as you do. I'm a member of technical staff at a company called Telitis. You can find me on my personal webpage at hack.org/MC as well, and my Gemini capsule, of course. This is not the Gemini, the AI Gemini, the other Gemini. Telitis, the company, was born at Mullvad VPN's trustworthy computing research team. And this is Mullvad's mascot, Cookie, building some kind of hardware. Foreshadowing here. The research department split into several companies, and now there's an entire group of them, apparently, and we are the hardware department. That's Telitis. And if you will bear with me for a minute, I will talk a bit about the hardware and where we are at and why we are doing the thing we are doing. So, this is the Telitis T-key, an open source hardware security token. And I probably don't need to tell this crowd what an FPGA is, but the large ship behind the ant is an FPGA, a ship you can download your own ship design into and turn it into another ship. It's an FPGA-based RISC-V computer for sensitive computations. There's no secure enclave, there's no black box, because it's fully open from chip design and circuit board all the way to applications. It still provides strong security, and it's all open source, and it's available on our GitHub repos. Everything is. There's also a developer handbook if you want to develop applications for this thing. You can visit it at dev.tilitis.se. You can use a T-key for authentication, digital signatures, signed if you want, random numbers, encryption, and other things, because it's a general computer in the disguise of a USB token. Inside the FPGA, we have a 32-bit RISC-V Pico RV32. Claire Wolf designed it. It's a soft core. We have some RAM, some hardware security cores, memory maps, so the CPU can use them. There's a security monitor for doing stuff with the address space, and 2 privilege levels. So if you're running in firmware mode, some of the address space is not available, and if you're running in application mode, I switched that. So in the application mode, some of the address space is not available, and in the firmware mode, everything is available, except one thing which is only readable once, and I'm going to get into that later. There are no interrupts. It's just a USB CDC, so basically a serial port, and this is the current platform. There's no persistent storage, but there is a 1 megabyte flash, which is available during hardware development, but not to store anything on when you run the applications. There is no operating system, just a small bootloader firmware, 4K or so. We are currently working on the next generation. It runs slightly faster. Instead of just being a serial port, it also has human interface device and CCID classes, so it's basically visible as a security token and a smart card, if you like. Depends on the app you run on it, though. The flash is now usable, so we also have a file system, and to access the file system, we of course also have system calls. So the small firmware turned into an operating system, kind of. And there will be a pre-installed device app on storage. So when you start it, it runs FIDO2. Yeah. We only use open source tools. So the chip design is in Verilog, and using Verilog with open source tools, all this limits the choice of the FPGA chip, because the entire backend thing needs to be available for the FPGA bitstream format, etc., etc. So we use Yosys and NextPNR. We use ice storms tools, and all this is reversed by Yosys themselves. So we developed NVCM programming tools. That's a non-volatile configuration memory inside the FPGA, so we can lock down our design inside the chip. We use Icarus and Verilator and KiCad. Everything is published, including the tooling we use, etc. The FPGA chip we use is the Lattice Ice40, which already had good support in open source tools, and it has the important thing with the lockable internal configuration memory. Since we lock down a hardware secret inside this, it's important that we can fuse this off. It has quite limited resources, not many logic cells, and we are at something like 94% utilization right now in the new generation, which is, yeah, on the edge. We are paying for reversing other FPGA chips, so probably in a future generation we might have more resources. Inside the FPGA, this is basically what it looks like. We have a CPU, we have some special firmware ROM, which is immutable, of course, because it's ROM, and this is important. We have an immutable boot code in ROM, which we implicitly trust because it's immutable and on chip. There's some special RAM for the firmware for doing sensitive computations before the application is started. This RAM isn't available by the application, only firmware. Then there's the all-important unique device secret, which I will talk about later. That's a base hardware secret created during provisioning and which will never leave the device. And then we have a small timer. We have some UART stuff for I/O with the client. And we have a touch sensor. And we have a random number generator. It's some form of oscillators. Some RAM and some other stuff, which isn't really important right now. Our own software is an emulator. It's a friendly QEMU fork, which is also available as an OSI image, which you can use to develop stuff on the Tiki, even if you don't yet have any hardware. It also supports the next generation already. There's a simple firmware, which is grown into a small operating system, all 8K or so of an operating system. There's some client applications, and the killer app is our SSH agent. There are client libraries to develop client apps in Go and Python, and a proof of concept in Java. This is what we have developed ourselves. There's also device libraries to develop applications on the device, mostly something sort of libc-like. And then there's the Tiki Builder OCI image with all the tooling to build everything, if you like. We have had some external people also contributing software, among them a Rust bring-up and sort of support for doing Rusty things. And we have a client library in TypeScript of all things, using Web Serial. And we had 2 independent bring-up of Zig on this platform. I'm see now that I've written TypeScript twice. Let's delete that. So, and TinyGo bring up by Ron Evans. TinyGo, if you don't know it, it's a version of the Go programming language and compiler. So instead of using the straight Go compiler, they use LLVM, and you can compile Go programs for this thing. There's also a Tiki Age plugin, which is a plugin to the Filippo Valsorda's Age encryption tool. Daniel, he was here yesterday, but I don't think he's here today. All known projects are listed on the developer handbook. The status of this thing is the first official hardware release was in March 23. There are several client apps available, development tools, and we have reproducible builds in place for most of the things, except client apps on Mac OS. I'm sorry. So everything is released on GitHub. But okay, how do you use this thing? I want to log into something, typically an SSH server on my own server, hack.org, or I want to log into GitHub or GitLab or sign my Git commits. I want to do a Git push, or I want to just SSH. Well, my client, and that's what we call the computer or the mobile phone you insert your Tiki into, has already started our own Tiki SSH agent automatically when I logged in to it. I insert the Tiki into my client, into my laptop. I do the SSH command. The agent automatically loads the device app signer, which signs ED 25519 signatures. The Tiki starts to blink the status LED. I tap the Tiki, and I'm in, just like any other security token, right? But this is a general computer. How can you trust a general computer? What if someone writes a device app which leaks the private key? Game over, right? There's no secure element, so the private key should be completely unprotected once someone just writes a program. Here is where the measured boot comes in. What if we don't share anything between device apps started on the Tiki and guarantee the software integrity by measuring the apps and creating a secret for this combination of this app on this particular device? And if you run a malicious app, you leak the secret, okay, fine. But you leak the wrong secret. And I'll have to define what measure means in this case. You compute a hash of instructions and critical data. You are about to start. You store the digest securely where no one else can update it, and then you allow the program to start. This is measuring in this context. And as you probably know, there are different measured boot systems out there. The TPMs, for instance, has a form of measured boot in the PCRs, and you probably know a lot more about TPMs than I do. 2,500 pages or so of spec. And then there's the device identifier composition engine, the DICE, originally Riot, much better name, from Microsoft Research. And this is what we were inspired by. So we use DICE-like measured boot, like this in the current generation. We have a unique device secret, the UDS, in hardware. That's something the user has, the device itself. There's a specific secret created on the device during provisioning, and it never leaves the T-key. Only firmware has access to this, and it's available only once per power cycle. Then there's an optional user-supplied secret, the USS, something the user knows. This is typically a passphrase or something typed on the keyboard or something, which we send over when we are going to load an app. And then there's the digest of the T-key device application itself, measured by firmware before the application is started. This is the integrity of the application. And then we compute the base secret that we leave to the application. That's called the compound device identifier, CDI. So we throw this to all these things, the UDS, the app digest, and the USS on a hash function, Blake2S in our case. And we get the CDI. This is the base secret that you can use to unlock other secrets. You can create new key material. In our SSH case, for instance, this is used as the base to create a key pair for SSH or any other ED 25519 signatures. And it can be hard to get this across. So I tried it on my daughter, Ylva. She's 16-year-old, and I discussed how we do it, how this works, and tried to explain it in a good way, and I think she got it because she drew this. So you use the immutable code, that's the cauldron. You hash the application to start, that's the carrot. And you mix in the hardware-specific secret, that's the magic potion in the rabbit bunny wizard's hand. And you get a new secret. Yeah. And I think she got it. So the advantages of using a DICE-like measured boot like this, it's much more lightweight than a full TPM. It's easy to implement. The software integrity is guaranteed. If you change the software, if you write something malicious, or if you just change it somewhat, you get the wrong keys. And the resulting secret can also be used to create new key material and unlock other secrets. If you want to use it for, I don't know, unlocking an encryption disk, for instance, you can do that. The private keys themselves are not stored on the device, so no storage is needed for sensitive stuff like a secret, because it's computed on demand. And since it's computed on demand, you can have an unlimited number of private keys. So you can just generate more keys or use different apps for different purposes, which get automatically different keys. And if you isolate the apps from each other and they don't share any storage, secrets can't leak between device applications. This is very different than verified boot, also known on some platforms as secure boot, because on a verified boot, you're verifying a signature over an app or an app digest against the publisher's public key. And forced verified boot would lock apps to a specific publisher of the app or the device vendor, and this, we think, is unacceptable in an open platform. And this is an open source product. We want it to be open. However, there's a problem. This is also a good thing, but it's also a problem. because the CDI and any derived key material will always change if the device app changes, including app updates, which is kind of bad if you want to log into your SSH server, right? So you update the app, or Debian does, and suddenly all your keys have changed. Damn it. And you can't log in anymore. Wow. Right, so we think we have a solution to this problem. So part one of the solution is we allow the chaining of apps with a reset in between. So we allow apps to reset to firmware bootloader and start again. But before resetting, we ask the firmware to measure something, let's call it app ID, which results after measuring in something called measured ID. And this can be whatever the app wants to be measured. If it just wants to leave its own secret somehow and then measure it, it can. But it can be something else, something like a security policy or a public key or anything. Then you reset and load a new app. That's part one. We also introduce domains for impersonation protection. Since we now allow different ways of starting apps, we introduce these domains. Started with or without user-supplied secret, directly started, or as this typo, part of a chain of apps. Not extremely important at all, just some basic sanity here. And then after the reset, we compute the CDI like before, but instead of the app digest, we use the measured ID, measured by the firmware from data left by the former app. So this is the new way of calculating the CDI. Like before, we use the user device secret, unique device. Less unique device secret, the domain, like I introduced earlier, then the measured ID instead of the app digest, and any optional user-supplied secret. That was the first part. The second part of the solution is we use an app for verified boot. So the first app that starts is a boot verifier, a verifier app. This in turn verifies the next stage, for instance, by just checking a signature over an app digest against the public key. And then we ask the firmware, the verifier app asks the firmware to measure the publisher's key as the app ID into the next CDI. There's some debate currently if we should use a combination of an app name and the publisher key instead of just the key. And I'm interested to know what you think about that. Then we reset and compute the CDI, like this. So instead of using the app digest, we have this measured ID. Otherwise, it's mostly the same. And after reset, we load the app as usual, compute, and compare if its digest is the same as the already verified digest left behind by the previous app, and compute the new CDI. Then we start the new app. And now the new app always has the same CDI, regardless of if it's updated or not, which means key material doesn't change. So what is measured now? Instead of measuring the application, as in the application digest, we measure the integrity of the boot verifier boot stages. It can be several, but in our example here, it's just one. And we measure the identity of the app in the form of the digest of its verification data. Right now, just the publisher key, but it could be app name or publisher key and publisher key. And the domain for impersonation protection. We are not necessarily interested in the publisher's identity. We just want to measure it, and we want it to correspond to some private key. Because if you use the wrong publisher key, this is still an open platform, so you can use whatever keys you like. But if you use the wrong publisher key, you get the wrong CDI, even if you use something where the verification works. So you use your own private key, your own signature, your own publisher's key, and you are going to load some app. You will get the wrong CDI compared to the correct app. So still the same idea. We use something to measure something to get a secret. And if the thing we are measuring is the wrong thing, we get the wrong secret. Same thing as before. Instead of using just a public key infrastructure, we could use an inclusion proof. Our sister company, Glasklar Technique, they have the SIGSUM project, which is a very elegant and simple transparency log of signed checksums. And I don't know if you know anything about transparency logs, but imagine certificate transparency, but instead of storing entire certificates or something, you store just a signed digest. So there's not a possibility of poisoning this log. You have to store the data somewhere else. However, if you add something to a SIGSUM log, you get a proof back. You can use the proof just like a signature and a public key. So you can distribute that with your software updates instead of using a signature and a public key. And then you can verify that this thing, whatever it is, has been included in the log according to security policy saying you trust this witness and this witness that this log is correct. You can do this entirely offline. You don't have to talk to the log. And this is interesting, and we wanted to use it, but our own hardware, the T-key, is too slow to use this just for starting a new app, because you have to wait for several seconds to get your FIDO2 app running, and that's not acceptable. It might be that we instead use it at the signing ceremony when we release an app with the sign if logged program. But we're still not sure about that, but possibly. Which means we can publish something on the log, like a release, a GitHub release, publish something, do a digest over the release, add that to the log, and then when we want to release it for real and sign the app, we can run it with a sign if logged program and an inclusion proof that we already published this, we released this. And not until that proof is correct, it will sign our app, which means we can still at least detect if our private key has been used, which means it has been leaked. So we would like to start all kinds of computers like this. Imagine if a T-key-like device was available on the motherboard. It had direct access to some small, static RAM, which the main CPU also has control over. And you have control over the reset on the main CPU. And before the first instruction even starts on the main CPU, you load and measure something in this small memory. A first stage bootloader, for instance, or something. And then, like the T-key, you provide this computed CDI or base secret to the rest of the thing. And then you start the next step. I would like this very much. It guarantees the integrity of the boot chain, and you can mix it with verified boot, like in this example before, and get integrity proof and verification proofs of everything. And it's much, much simpler than a TPM. So, in summary, our project uses dice-like measured boot to guarantee software integrity and create a base secret, the compound device identifier, like this. But the device apps can't be updated without changing this CDI secret. So the solution to our problem, we think, is we introduced chained apps and a domain to differ between chained and directly loaded. We combine the use of measured boot of a boot stage, which in turn verifies the next stage. We give the next app a secret based on the trusted measure of verifier's CDI, its own secret, and an app ID. And app ID is just the Blake2S of the publisher key, or the Blake2S of an app name and a publisher key. And then we compute measured ID, which is the Blake2S of the verifier's own CDI and the app ID. Then we reset and compute the next secret like this: the unique device secret, the domain, the measured ID, and an optional user-supplied secret. Throw all that into a Blake2S, get a new secret, win! The main repo is on GitHub/deletis. This is the hardware and firmware repo. We have a threat model of the upcoming generation, much updated. There's a repo for the boot verifier device itself. And please have a look, and please bring some feedback, because this is an open source project. All of it is published. We welcome PRs, and if you feel inspired to use this in something else, please go ahead. If you like, please tell us. But you don't have to tell us. So, if you want to talk directly to me, please mail me. I'm also on IRC, on our Telitis channel on the OFTC network, and unfortunately also on the Matrix. It's bridged. Our main web page is telitis.se, and we have this developer handbook on dev.telitis.se. The Castor part of the developer handbook is very much a work in progress, and again, that's also open source licensed, so PRs and issues are welcome. Thank you.
Any questions for Mikael?
Is it on? Yeah. This USS, the key,
Yeah.
I'm not to follow that really, because you're using this thing to get secure boot. And how do you get in this key without having the system booted?
I'm not sure I understand the question. Can you?
You need to boot the system before you can put in the key.
Well, the first thing that is booted is the key.
Yeah, the USS, the private key.
Oh, right. Okay. Oh, now I understand. Oh, that's a miscommunication perhaps, but because there's two systems involved here. There's the laptop, or what we call the client.
Yeah.
And then there's the T key. And if you want to run, for instance, the SSH signing thing on it, then this part is the trusted world, the T key.
Yeah.
And then you have the client.
Yeah.
And the client is not necessarily trusted. And it's just a user interface right now. So if you want to get the user-supplied secret, which is typically a passphrase, or something which you type, then you can be totally owned on the client.
Yeah, but you talked about get it integrated in the motherboard.
Yeah, but then perhaps we wouldn't use the USS itself. I said it was optional. So if we integrate this thing on a motherboard and start all computers like this, I think it would make sense not to use a USS at all. Yeah. Sorry for the confusion.
So for the second stream you had, where you're using public keys of the app, that sort of implies that anything that's signed with the same public key will be able to access the same secrets.
Correct.
So
that's why we are currently debating if we are also going to use an app name and the publisher's public key. So which means currently it means you have to have different public key for different apps from the same publisher.
Yes,
Yeah.
but this should be a policy thing, right? The app, like some publishers would like to share secrets between two different
Yeah,
apps, and some
yes.
would. But so my other question was, do you have any thoughts on what happens if the private key is compromised? You don't have any way to revoke stuff here,
No.
right?
No.
Okay,
No,
so
currently, no way in the system itself to revoke a public key or something. But if it's used like this, well, it all comes down to software distribution, as usual. So the original T key only allows you to load something from the client. So if someone sneakily installs something on your laptop, which, well, let me back up. Say the private key from the publisher is leaked. We can't revoke it. It's always going to be used as something to create a new secret, right? And people have registered with this on web services or SSH servers, etc., etc. And it's still the same problem as everyone else has when it comes to distribution of key material and software. The SIGSUM transparency log would help, because then you can notify yourself as a publisher when the private key has been leaked. So a transparency log and using the sign if logged, for instance, would help. Then you can notify users about this particular software or this particular public key is now compromised. Please update to a new public key.
But is there a way to invalidate the state on the device? So can you, like, I'm running an app from someone that was where their private key was leaked. Can I then sort of invalidate everything that's on the device so that this key can never be used to gain any secrets, or do I just have to sort of go and remove the public key from all the SSL?
To remove.
Yeah, so there's no state on the device that can
no,
be wiped,
no,
anything.
Not so far. And if you find out the way of doing that in a nice way, please get in touch.
All right.
But the obvious real solution to this problem is to use not just the public key, but also inclusion proof, and force all the users of all the publishers of software for this thing to always publish them in the transparency log. Then everyone could monitor that and see if the private key has been leaked, and then immediately take action. But currently the T key is too slow to do that verification. Maybe in the future.
So, yeah, it seems that's a big risk you're taking for the possibility of updating. Is there a way of, like, saying, designing your app in some way that it cannot be updated even if the key leaks?
Yes.
Okay.
There is, because we are still allowing direct loading, just like the current version of the T key doesn't have this system at all. The current version you can buy right now is always directly loaded, and you can't update the app. And that system will still be in place on the next generation. So if you want to use a direct measured application, you can, even in the next version, the caster version of the T key, which means you can't update your app at all without changing all key material. And some people would like to keep it that way, and the system is completely open to do that as well.
Any more questions?
So this is all really amazing with all the open source and using the reverse engineered tools for the FPGA. It seems like a lot of effort, and I'm wondering and curious, like, who is paying you? Who's your customers? How do you get money to do? I think it's great work, and I can see why you want to do it, but, like, how do you make that happen?
Well, the answer is a mix of some very interested customers and some very, very profitable sister companies, Mulbot VPN.
I see, thanks.
this would obviously be fun to play with. So where do I get this? How do you get to a device? Do you have a web?
Shop.tilitis.se.
How much is it?
I think right. 880 Swedish.
Any discount codes for us?
I actually have one with me, so if you don't want to pay for the sending of the package, you can use a code you get from me, and you can get it from my hand if you buy it.
All right. Thanks a lot.
Thank you.